Hello, today we're going to be working with the synthesis of dibenzylketone. This molecule is not present in your book and is rather found in the following paper. The information is provided in blue. It is very important that you pay attention to this particular presentation as it is very, very experimental, and we will try our best to explain to you the procedure. So this is the reaction scheme. We're going to be working with 2 molecules of phenylacetic acid and 1 molecule of iron in order to make dibenzylketone, and a couple of byproducts like hydrogen gas, carbon dioxide, and iron oxide. This is the setup. So we're going to be explaining it very carefully. Over here in red, we present the 3-neck round bottom flask. This is where the whole reaction is going to occur. This thermometer over here is going to monitor the temperature of the reaction. We're going to be making a distillation. So this other thermometer over here is going to be monitoring the temperature of the distillation, which is the second part of our reaction. In green, we show the round bottom flask where our product is going to be collected after the distillation. Following the yellow, we show the hoses. So this reaction is going to generate gas, as we had seen before, hydrogen and carbon dioxide. The gas is going to follow the line over here, and it's going to arrive to this container that it's a trap. This then follows the next hose, and it's going to arrive to the container that it's shown in blue. The container is going to be full of water, and as the gas traverses through the pipes, we're going to be seeing a lot of bubbling from here. First from hydrogen gas, and then from carbon dioxide. So it's really important that you really picture this part over here, as it's going to be the way that we're going to be monitoring our reaction. The procedure is the following. We're going to add 35 milligrams of phenylacetic acid and 8 grams of iron to our 3-neck flask through the center neck. So once your instructor inspects the setup, we're going to use a transformer that's specific for this setup. It's not pictured in the following slide, to 50% the voltage, which is going to generate a lot of heat. For safety, the sash of the hood should be lowered and the transformer is placed in the next hood. You will monitor the progress of the reaction by collecting hydrogen and carbon dioxide by displacement of water. Now, it's really important that we picture again in blue our water container. So here we show the end of the hose. We're going to be showing it in red. So the end of the hose is going to be holding all the gas, and it's going to be bubbling. So what we're going to do is we're going to take a cylinder. We're going to fill it up with 30 ml of water, and we're going to set it up inside the container so that in this position that it's inverted, we're going to still have our 30 ml of water and 70 ml of air. So the bubbles are going to be introduced inside the cylinder, here marked in red, and by displacement of the volume, water is going to come out from the container that already has water, and little by little, here in the arrow in green, our cylinder is going to now have 30 ml of hydrogen and the 70 ml of air that it already had. So as this happens, you're going to notice that your cylinder here in purple is going to be it's going to look like it's empty. It's actually full of gas, but you no longer will have water. And you will actually see the bubbles just, rounding up the mouth of the cylinder and not really getting inside of it. So this is when you know that you have generated hydrogen inside of your cylinder, and this is the way that we will monitor our reaction. Once the liquid is completely displaced, we will set fire to the mouth of the cylinder and ignite the hydrogen gas. So pay attention to the following video where we show one of your previous classmates performing the experiment. You could see that the cylinder is dipped inside of the water and it's already full of the gas. So one student is going to pull out the cylinder and the other one is going to ignite the mouth of the cylinder.
this hydrogen is softer than the air, so it's not.
The noise is actually very funny, and it makes everybody in the room go impressed because nobody's expecting it. So eventually the gas explosion will cease, and that way we will know that the second part of our experiment will take place. Here we show the mechanism of reaction. So first of all, here, let me switch to this. Here we will have our metal. That metals, as you may know, and acids make hydrogen gas and salts. So for example, here it says palladium, but it's actually lead. It's Pb. So lead and sulfuric acid made lead sulfate and hydrogen, and this is and a spark makes your car battery blow up. The same is true for sodium and water. If somebody has actually seen it in YouTube, you will see that the thing you're going to generate is sodium hydroxide and hydrogen. But due to the exothermic reaction, you generate enough heat in order to ignite the hydrogen. So the electron transfer from a metal to the sigma antibond of a hydroxyl group makes a radical anion that splits into a hydrogen radical. Here we exemplify it. Here we'll have the hydrogen radical and an oxide. So hydrogen radicals combine to make hydrogen gas over here, and the oxide combines with the metal in order to make metal oxide and hydrogen. So here we show it an example with our molecule. We're going to have our two molecules of phenylacetic acid and iron, and as the reaction occurs, we're going to be generating hydrogen, and we're going to be generating this iron intermediate over here. The second part of the mechanism is, and let me remove the, okay, that's not. So the second part of the mechanism is the following. So over a period of heating, we're going to have a rearrangement over here. So our molecule is going to actually make a resonance structure. It's going to tautomerize, and the double bond is going to attack the carbonyl over here, and it's going to generate this six-membered structure ring over here. Then it's going to be unstable and it's going to collapse in itself. Overall, the arrows of the mechanism will generate iron oxide. We're going to generate carbon dioxide. We're going to generate also a proton that it's going to make an acidic solution. And we're going to be generating our dibenzylketone. This is actually the enol can undergo an intermolecular Claisen condensation to add to the other carbonyl and eliminate the iron oxide and carbon dioxide. So the extra proton combines with the enolate to make the final product. So once we cease to listen to hydrogen combustion, we will start increasing the variable transformer from 50 to 100% voltage, 1% per minute. Carbon dioxide should start evolving as no more combustion will be seen. Once you reach 100% voltage, dibenzylketone should start distilling. So once the dibenzylketone is distilled, carefully weight the distillate and distribute the information to the class. Remember, everything is around 400 degrees, so extreme care must be taken. The whole class should disassemble and clean the reaction setup. Remember that we're going to be performing IR and NMR spectroscopy to our molecule.